In the final video of this short series about nonlinear op-amp circuits, I want to have a quick look at a couple of fun little circuits which can do some interesting maths. We'll start with this one. Now, you can analyse this circuit in the same way that we analyse the inverting amplifier. The op-amp will try and maintain both of its inputs at the same voltage, in this case ground, and that means that the current flowing through the resistor here will be A minus 0, the voltage across the resistor, or just A, divided by R. That current then flows through this diode. Now we can use the Shockley equation to relate the current through the diode to the voltage across the diode, and note that the voltage across the diode is minus X, because at this side of the diode we have ground, 0 volts, at this side of the diode we have X, so the voltage across the diode will be 0 minus X. Put those expressions into the Shockley equation and we end up with this expression here, which means that we have A over R equals IS, the saturation current, times e to the power of minus x over 25 millivolts times n minus 1. Now, in the case where x is a reasonably large number, e to the power of minus x over 25 millivolts times n is going to be much, much bigger than 1. Remember that x is a negative quantity, so minus x is positive. In these situations, we can afford to neglect the minus 1 and just approximate our circuit behaviour like that. That would mean that we have exp of minus x over 25 millivolts times n is equal to A over R times IS. Or take the log of both sides and multiply up by a few things. X equals minus 25 millivolts times n times the logarithm of A over R times IS. We have a circuit here in which the output appears to be proportional to a function of the logarithm of the input. Now, if I had an input here, I'll call it Vin, if I put that through an amplifier, which amplifies it up by R times IS, and then I put that into my circuit here, so this is A and this is X, and then I put the output of my circuit through another amplifier, this time with a gain of 1 over 25 millivolts times N, and call that my Vout, then the circuit that I've produced has a very simple and interesting property. Vout would be minus 1 over 25 millivolts times N times X, but X is minus 25 millivolts times N times the logarithm of A. Well, A is R times IS times Vin over R times IS. That cancels with that with that minus cancels with that minus, the IS's and the R's cancel. We just end up with Vout equals the log of Vin. We can build these circuits quite readily. They're just amplifiers with constant gains. So, we have built a circuit which will give me an output voltage which is the logarithm of the input voltage. We can go the other way as well. Similar argument. The current flowing into this circuit here through this diode is going to be related to the voltage across the diode, which is just the input voltage A, by the Shockley equation. So the current flowing in, IS times e to the power of A over 25 millivolts times n, the ideality factor of the diode, minus 1. And that is the current that's flowing through this resistor here. But we can also express the current flowing through this resistor here in terms of the voltage across the resistor and the value of the resistance. Well, the op-amp will be keeping its two inputs at the same voltage, in this case ground, So the voltage across this resistor will just be 0 minus X or minus X. And the value of the resistor is R. So we get this expression. Now once again, if A is a reasonably sized voltage, then e to the power of A over 25 millivolts times N will be much, much bigger than minus 1. We can afford to neglect the minus 1. And here we would end up with X, our output, being minus R times IS times e to the power of A over 25 millivolts times N. And as before, we can build this into a larger circuit. We could have an input voltage here going through an amplifier, and the amplifier makes that bigger by 25 millivolts times N. That feeds into our circuit here, input A, output X, and that feeds into an amplifier with a gain of 1 over R times IS, giving me V out. Now, V out is equal to, sorry, that should be minus 1 over R times IS. V out is minus 1 over R times IS times X. X is minus R IS times e to the power of A over 25 millivolts times N. But A is 25 millivolts times N times V in. And once again, just about everything cancels, and we end up with V out equals e to the power of V in. We have a circuit that takes antilogs. So we've now got a circuit which can take logs and a circuit that can take antilogs. Right. What does this do? Well, X, our output, is the antilog of the difference between the log of the input A and the log of the input B, which is the antilog of the log of A over B, in other words, A over B. We've built a circuit that can divide two voltages and give an output which is the ratio of two input voltages. And you can actually buy little analog chips which have exactly this function. It's quite useful in analog computations. Of course, if we replace the differential amplifier with a summing amplifier, we could make a circuit which multiplied together two inputs. And those circuits have a lot of applications. They're sometimes called mixers. And that brings us to the end of this short series of videos about nonlinear op-amp circuits.